Managing soil carbon. Derek asked me to talk about carbon today. There's a lot of things Dr. Lyle talked about that would be really fun to follow up on, but we're going to focus on carbon today. And I'm going to agree with a number of things that Dr. Lyle said. I thought it was a really excellent presentation, and that I will part company on a couple of points, and we'll come back to that at the end. But using the Hippocratic Oath, first do no harm, is something that I think we need to keep in mind all the time, because I think some of the biggest challenges we're going to face moving into the future with a warming climate is keeping the carbon in the soil that we have. So with that, this was just published in Tree Hugger a couple of days ago, and fits well with Ratan's talk. Could better soil management reverse global warming? And the article goes on to suggest that storing carbon in soil would play a major role in reversing this trend. And I think that's really wonderful and hopeful thinking, but we have to be scientists. We have to be realistic about what we can and can't accomplish with soils, especially in the time frames that we're talking about with regard to climate change. What are we up against? I thought Dr. Lau did an excellent job of presenting this. The population is exploding. We're at 7.3 billion currently and counting. If you ever turn on the world clock and watch the world population clock and watch it tick, it's a little disconcerting because the death rate is falling behind and the population rate is growing. And with that, we have an increasingly urban, thank you, Derek, we have an increasingly urban populace. In the United States, we're up to 80% urban and growing theoretically at a rate of about 1.2% per year. Fossil fuel consumption is expanding, it's not going down, and land clearing continues, although the carbon emissions associated with land clearing are declining compared to what they would have been over the last century. So this is one of those the hockey stick figure that most all of you know and know extremely well. The temperature change is very consistent over the last 1,000 years, and then with a lot of variation, and then starts to climb with the Industrial Revolution. There's, as Dr. Lau had suggested, the Anthropocene probably started 8,000 years ago, is the truth of the matter, as land clearing has been occurring all throughout this period, with noted demise in civilizations all throughout this time frame. Now, with the Green Revolution and with changes in agricultural practice, we're able to catch and reverse some of the negative effects of our poor management. And that's something that Dr. Lau talked about at the end, too, of the benefits that will have moving into the future. Where is the carbon coming from? Well, here's where I'm going to part company a little bit with Dr. Lau. The fossil fuel burning is currently accounting for about 9.7 petagrams of carbon emissions per annum. And deforestation ranges somewhere between 1 and 2.5 petagrams of carbon per year. The sinks are ocean and terrestrial, and these are historically in good balance with emission rates, but with our fossil fuel burning rates and with land clearing rates, we've well outpaced the capacity of oceans and terrestrial sinks to capture all of that carbon. The storage is in the atmosphere, biomass, and soils, and these historic estimates of about 1,500 petagrams being in the soil are considered to be gross underestimates as we dig deeper and deeper into the soil and recognize that there's a lot of carbon at depth in soil. As a matter of fact, Tarnakai, who studies circumpolar soils in particular, has identified 1,700 petagrams in the circumpolar region alone by going down to 2 to 3 meters depth when calculating total soil carbon. So revised soil carbon estimates should probably go up. Where are the carbon reserves with regard to fossil fuel burning? This is where the problem exists. Where we have a lot greater problem with fossil fuel burning than I think was presented in the last talk. And I say that because here's our emissions to date. This is from Jim Hansen. It's a few years out of date. 200 gigatons or petagrams of carbon as coal emitted over time, with another about 100 of oil and maybe 20 of gas. Here's our reserves of coal. Here's our reserves in shale oil and tar sands. These are going to cook our goose. We're only at 400 ppm of carbon currently. This figure here is the remaining fraction of CO2 in the atmosphere versus time. It gives us a sense of the half-life of carbon dioxide in the atmosphere, with about 33% remaining in the atmosphere after 100 years' time. So the carbon emitted doesn't go away tomorrow. If we don't slow the rate of carbon emissions from land clearing and from fossil fuel emissions, we are absolutely going to cook our goose. And when we look at these types of reserves, we recognize that there's a lot more carbon to be emitted if we don't change our consumption patterns. Mitigation, how are we going to mitigate climate change? Fossil fuel carbon is geogenic carbon. It's buried below ground, and it's in a form that would not be emitted 90%, 99% of the time if we didn't drill, process, and burn it, okay? Soil carbon is cycled carbon. It's part of the active carbon cycle. If we disturb soils, they emit soils. If we build soils, they store carbon. And so soils have the potential to release more carbon under poor management and have the potential to store some more carbon under proper management, which we'll talk more about. We also talk a lot about afforestation and carbon sequestration. But when we talk about afforestation, we have to recognize, exactly as Dr. Lau said, we're talking about recapping what we lost from land clearing to a great degree. Afforestation is really reforestation in a number of cases, or revegetation of the landscape. We're recovering what was taken out of the soil and out of biomass, and we have to consider that in addition to the carbon that's being emitted with fossil fuel burning. So, soil management. First, do no harm. This is a figure or an image from La Gomera in the Canary Islands. It was agricultural land that started to erode and erode rapidly during the wet season of the year. And they attempted to restore and stabilize the soils with eucalypts, eucalypt plantation. And you can see the rate of soil loss here are the roots of the eucalypts from just about 20 years' time being lost to erosion, and with it all the fertile surface soil and carbon. So our soil management has to be done right. So let's talk a little bit about carbon. Carbon is, from a soil scientist perspective, from our perspective, is so much more than just the source of CO2 into the atmosphere. It's the currency of life in soils. It's energy, it creates soil structure, it's digestive tissue in terms of the microbial organisms and respiratory tissue that's associated with a living soil animal. And these natural ecosystems that what originally exist on these landscapes really define the capacity of those systems to hold carbon. That is a benchmark telling us this is what the soil could effectively yield in terms of total carbon storage in a system that was basically closed. We have to keep in mind that agricultural systems are open systems. We're exporting grain, we're concentrating it in urban centers, and we're not returning those nutrients to the landscape. That's why the humus production that Dr. Lau's talking about is stalled out, because of the nutrients are all being put into the landfill, and only in certain cases are they put back on the landscape. If we manage for soil health, we will store more carbon. If we manage our soils as us soil scientists would like to envision, we would store more carbon, but we shouldn't expect it to save us from our gluttony. When I say gluttony, I mean the consumption of fossil fuels as a energy source. We have to think bigger. So, In this talk, I was going to talk about a few examples. I'm going to talk a little bit about temperate forest systems, then boreal, and then a little about Great Plains grassland ecosystems and carbon loss. So this is an image from Western Washington, from about 1970, and demonstrates the type of timber harvest that was going on in the U.S. at the time on federal lands. Removal of one rotation of carbon from a soils perspective in the short term isn't a big loss, but in the long term will represent multiple rotations, potentially will represent a significant loss. The other issue is soil erosion rates, open canopy, increased surface temperatures. That leads to more rapid decomposition of soil organic matter, but you have also just introduced a whole lot of residues, as you can see all across the surface, that are decomposing. So in the short term, you actually have an increase potentially in surface soil organic matter, but then it ultimately decreases due to rapid decomposition. This just is an image that we see frequently with regard to afforestation and the accumulation of carbon and what we might be able to do with afforestation. And I'll just point here is the tree biomass. This is from McKinley 2011 Ecological Applications, and it shows the increase in biomass, carbon being stored into the system. And then here's a timber harvest, and we have an offset of biomass energy, we have a substitution of fossil fuel energy, we have substitution also of cement with wood, or building products with wood products, and we store carbon in products, as well as this is the forest litter then decreasing a bit and then increasing over the next cycle, and then and the soil or mineral carbon staying relatively stable. But the thing to keep in mind is that this is starting from a point of zero forest biomass. Here, if we start with a forest ecosystem, harvest the timber, we have this significant drop in biomass carbon. Some of it is stored, some of it is offset, but it is a net loss of carbon from the system. And we have to keep that in mind. You can see the soil litter is dynamic and is changing with that process, but the mineral soil carbon is relatively stable.